Hello YouTubers, hope all of you are well. Dave out in Western Pennsylvania, USA. I work with bench scale supercap prototypes with focus on deep eutectic solvents, ionic liquid solvents, and selected electrolytes. I'm really focused on graphite materials for use as electrodes and how they will pair with the DES and IL solutions. Now, what we have here, just to show you, because we'll be preparing conductive inks, airbrushing, aerosol delivery of graphite, hopefully at the I don't know about nanomolar, but hopefully scale. Here's a piece of paper towel. And here is that same type of paper towel where I have deposited on it, I hope you can see the bottom of it too, we've deposited commercially available aerosol graphite. And this is sold by AerosolGraphite Industries. You can find it on Amazon. I've had good results with it. Toolmates. So what we're doing in one aspect of our work is putting some conductivity into this paper towel. We like the idea, of course, of it being very light mass and a supercap, which is important. And here are some numbers on this. Using a multimeter, I measured the resistance in ohms at 1 centimeter distances at points throughout the top and the bottom, the front and bottom. And it is kicking out values such as 0.09 ohms per centimeter, which is about the same as commercial graphite that we work with. Now, some numbers again. The paper toweling was 0.160 grams before any deposition. It's important, of course, how you apply the spray. And what we do is back and forth one side, let it dry 15 minutes. Now, the manufacturers say give it a minute, but I can smell the solvent. And I don't know what solvent they're delivering this with, but I give it 15 minutes to dry. Then apply a second coat uniformly at a distance of 12 inches. We try to be consistent. Another 15 minutes. Flip it around, repeat the process. Now, after being left alone for about an hour, when I left, it was at 0.224 grams. It started at 0.160. We left it overnight. The next day, constant mass reading 0.214 grams. So we have about 54 milligrams of graphite in principle on the paper. There will be some plastic binder, of course. But I like the resistance. This is, for our purposes, conductive enough. Now, we're also going to spray this on carbon paper, and which is conductive, but that's another story, another experiment. So, according to my calculations, there's about 25% at best mass graphite on the front and back of the paper. Now, in our approach, we have defined wet and dry circuits with graphite materials. Dry, if in a circuit, and we put it in with a lithium ion at 3.7 volts, we bring it up to about 4.1 volts, and we do cycles, as many as 100 cycles of charge-discharge. I have videos on that. But I want to pair that type of study using a power supply, a DC power supply. Now, I have uploaded a video, and this is a reliable, a very affordable product at $35 US dollars, and of course plus postage. And you can do constant voltage, constant current. And you can see right now I have constant voltage being used. In my prior videos I had constant current, but there are reasons why we want to go with constant voltage here with our study. So we have a constant voltage of 4.0 volts, excuse me, and the electronic load is an LED rated for 5 watts. And you can see that I have inserted into the circuit, I'm using a breadboard for convenience. I don't move this around. We have inserted into the negative lead the piece of graphite. It started at 0.16 amp. In about an hour's time, it's down to 0.13 amp, which means the resistance is being lowered, which is good. Very good. I'm going to let this go anywhere from 1 to 3 days. Now I'll come back to why I'm doing constant voltage with the power supply. Now, what will follow will be experiments, plastic holders with graphite felt, and in there is a piece of cotton. It's on the back, which you can't see easily. It's a piece of cotton which has been sprayed with the aerosol graphite. I'll be running that next dry in the DC circuit. Now, I've already done 75 cycles of charge discharge with the electronic load and the lithium-ion battery. And I have the files. I'll put them at my website so you can get the data. But the coulombic efficiency using the electronic load approach, pretty darn good. I think I zeroed in after 75 runs. It was running about 0.053, 0.052 or 3 for the capacity values for constant voltage charging and constant current discharging. So that looked pretty good, and that's simply for the dry material in that plastic case. Incidentally, it was tightly sealed. There was no mass balance before or after the 75 cycle run over 18 hours and about a minute and a half. So we will be running that unit at constant voltage for 1 to 3 days to observe what happens dry. And then I will, with my undergrad student, apply selected deep eutectic solvents with lithium tetrafluoroborate, borate, LiBF4, and even lithium bromide, which we have found will dissolve readily in selected DESs. So first we'll run this piece of paper towel. That may function as an electrode. We're even going to try to do a light amount of nickel plating on it, electroplating. We'll see how it holds up. But that'll be a different application. What will be important is to run this one in the DC power supply at constant voltage, and then repeat with the soaked graphite and cotton. The cotton being there to absorb the DES, and I can press it into that graphite before the run. And then we'll do another 75 cycle run of charge discharge. So that's where we're at with this. And why do we want to use constant voltage here versus constant current, which I was doing before? Notice it's at 0.14 right now. So we'll keep an eye and see what's going on early on. It makes more sense to run the experiment at a constant voltage, let's say 3.7 to 4.0 volts, and observe the current changes as an indicator of the DES solvent chemical changes or evaporation, especially for certain types of degradation mechanisms. Now, there are advantages of constant voltage. potentiostatic mode. Direct link to electrochemical processes. Sensitivity to changes in conductivity and interfacial resistance. Chemical changes, evaporation. Mimicking supercap operation to some extent, because supercaps, you know, accumulate charge at an interface under an applied voltage. So this setup isn't a true supercap, but holding the voltage constant is more akin to how a supercap is held at a certain potential, right? Potentially fewer artifacts and polarization. Now, what to look for in the current data. If there's a gradual decrease in current over time, a slow, steady decrease in current at constant voltage could indicate a gradual increase in resistance, right, due to chemical degradation, film formation, or increased viscosity due to evaporation or leakage. Sudden drops in current. Abrupt current drops might suggest a rapid chemical reaction that consumes charge carriers or the formation of a significant insulating layer. So I'm keeping my eye on this current right now. I wouldn't say it's a massive drop from 0.14 to 0.12 amps, but nonetheless, we're watching it. Nonlinear current changes, and the rate of current change might not be linear, reflecting the kinetics of the degradation or the evaporation process. Comparison to a control with a known stable DES electrolyte under the same constant voltage. So we're going to do comparisonal studies. More directly related to electrolyte properties, constant voltage. And the list goes on, but we're going to be uploading this data and keeping you informed on our research. Thanks for watching. Bye for now.